of symmetry, but it will also have laminates with elastic symmetry and properties of the anisotropic the use of composite materials in aeroelasticity gives place to a domain called aeroelastic tailoring. In aeroelastic tailoring, we try to improve the aeroelastic response of our system by modifying the properties of a composite material. It could be either in the orientation of the layers, the thickness of the layers, or even their material. For example, here in the example of the swept forward wing of the X-29 aircraft, we could gain 37% on the divergence speed by doing the aeroelastic tailoring of the structure. Ils n'entendent pas? Ok. Merci. So as I was saying, the aeroelastic tailoring started. One of the main first studies was done on the X-29 in the 80s, but then more studies continued on and on different structures. They mainly use as optimization variables either ply angles, which are the orientation of the fibers on each layer, but they could cause some limitations and drawbacks. For example, they are limited to a small number of plies because when using ply angles as optimization variables, we associate one variable to each ply, and we could increase these number of variables to a certain point. So it could be limiting in terms of our optimization algorithm. And they give place to a very non-convex problem, so it is very hard to obtain an optimal solution. In order to remedy these types of problems, a lot of researchers try to use lamination parameters, which are a set of mathematical formulations, parameters, that can describe the behavior of a composite laminate. But they also have their own drawbacks, such as they are generally limited to identical plies in material and thicknesses, or they are limited to only working with symmetric and uncoupled laminates in general. So the objective of our work is to overcome these types of limitations that are present in other works and try to even push further to formulate a general optimization formulation. To do that, we first need an aeroelastic system that is made of a structural and an aerodynamical model that are then coupled and solved in order to predict our instabilities. We will use parametric formulations such as polar parameters that also describe the behavior of the composite structure, but they are not limited to identical plies or to symmetric and uncoupled laminates. Using these models and formulations, we will conduct a deterministic optimization at the beginning, during which we try to improve the aeroelastic behavior of our composite structure. We will then consider uncertainties over the optimal cases and conduct an uncertainty quantification analysis. And finally, we will do a stochastic optimization which mainly combines these two steps by taking into account the parametric uncertainties during our optimization problem. So I will start by explaining how our model is constructed. As I said, we use a composite laminated plate wing. We consider 16 plies in this laminate. Here I have a straight configuration illustrated. That is a very common case in literature, particularly in the thesis of Christian Nischk, who was the PhD before me, whose work I continued. He worked with simpler models for both structure and aerodynamics. For example, he used Rayleigh-Ritz methods or quasi-steady methods for aerodynamics. We try to improve these methods by using the finite element method or the doublet lattice method that are more medium fidelity models and more common to use in industry in the pre-design step. And finally, the composite structures are modeled using the classical laminated plate theory. The fact that we use finite element method allowed us to study different configurations such as swept backward wing or swept forward wing. So here we have a representation of the equation of our coupled motion. On the right side we have the structural part, and on the right side we have the aerodynamic forces that depend on the displacement, velocity, and acceleration of the structure. So we can say that we need two separate models, structural and aerodynamical, in order to model the aeroelastic system. So I have two separate meshes, two separate discretization of my wing that need to communicate from one another because they are not superposed. For the structural part, I use finite element methods using the Phoenix library in Python, which allows me to obtain the mass and the stiffness matrices using the kinetic energy and the potential energy. On the aerodynamic model, I use the doublet lattice method, which models subsonic unsteady flows using the potential flow theory. It is mainly based on describing the vector of pressure coefficients as a function of downwash vectors given a matrix called aerodynamic influence coefficient matrix. The downwash vector can be expressed by the temporal and the spatial derivatives of my displacement, but I have to first calculate and compute these displacements using my structural analysis. I conduct a model analysis that allows me to calculate the structural frequencies and mode shapes that will then allow me to construct my displacement in different directions. But in this work, we are only interested in the vertical displacement. This is why we only keep the H components of our matrix phi that allow us to express the vertical displacements. I will then use a projection over the modal basis in order to communicate between the two meshes from the finite element mode mesh to the downwash point here at the 3/4 of each doublet lattice method panel. Using that, I can then calculate my vector of aerodynamic forces and rewrite the equation that I had at the beginning under the form of the modal matrices with the modal mass matrix, modal stiffness matrix, and the generalized aerodynamic matrix that were obtained by multiplication of the mode shapes. Once I have my aeroelastic system, I need to solve it in order to predict my instabilities. In order to do that, I use the PK method that is a very common aeroelastic solver, very easy to code. What it does is that it transforms my equation in the Laplace domain by imposing small perturbations. Here I have the similar equation that I had earlier, but with the real part and the imaginary part of my aerodynamic matrix that are separated. Something that is important is to notice is that that S here depends on my velocity of my flow velocity, my flow speed. So to solve the system, I augmented in order to obtain a first-order system and then solve the eigenvalue problem of my system that gives me complex conjugate eigenvalues where the real part represents my aeroelastic dampings and the imaginary part represents the aeroelastic 0 and flutter if the frequency is non-zero. But sometimes for the velocity that I chose at the beginning, of my system, I could never have a g that is equal to 0. This is why, if this is the case, I need to increase my velocity and reiterate over my system until I obtain a damping that is equal to 0, thus an instability. Here we have an example of a straight composite laminate. I first start by, in order to predict its instabilities, I start by defining an interval of velocity in between its flying regimes, here between 10 to 30 meter per second. And I solve my aeroelastic system for multiple steps, and I obtain the eigenvalues. Here we have the aeroelastic damping plotted against the velocities, and the aeroelastic frequencies against the velocities as well. On the diagram of the aeroelastic dampings, we can see that we have two instabilities, two modes that become unstable. First aeroelastic mode and the third aeroelastic mode. If I go back to the diagram of the frequency, I can say that the first aeroelastic mode gives place to a divergence instability, and the third aeroelastic mode gives place to a flutter instability because the frequency is non-zero. Here we have the representation of the two aeroelastic unstable modes at their respective velocities. We can see that the divergence mode resembles exactly the first structural mode, but the flutter mode does not resemble any of the structural modes that we have here. But if we look at the values of the frequency, it is in between the second and the third structural modes. And if we look at the shape, it is a combination between these two modes. So the flutter mode was obtained by coupling between the second and the third structural modes. So if I go back to the first color triangle that I had, now I have all three forces obtained by my aerodynamic, my stiffness, and the mass matrices that were coupled and solved in the Aeroelastic solver PK and gave place to my complex eigenvalues. But up until this point, I never talked about composite materials. I use the classical laminated plate theory to model my composite materials that allows me to obtain the rigidities corresponding to the material that I'm studying, and then allow me to calculate my stiffness matrix. What is the classical laminated plate theory? For a given composite laminate with a given number of plies, orientation of each ply, and then elementary layer stiffness, Q, I can express the internal forces as a function of the deformations using three stiffness tensors, membrane stiffness tensor, bending stiffness tensor, and the coupling between these two tensors. In my study, I consider a case of pure bending, so n is equal to 0, so I can rewrite the system under this form as a function of the curvature and a combination between the three other tensors. This combination is called the modified bending stiffness tensor detailed, which I will use during the rest of this work. But something to notice is that all these tensors here depend on the orientation of each layer, and they need to be shifted with respect to the reference frame. This is why the Cartesian method is not adapted to work with using the anisotropic material. So we try to work with polar parameters that are invariant to our reference frame. They can express any given plane tensor, either Q, A, B, D, or even detailed. As I said, they are invariant to the reference frame, and they are constructed of two isotropic moduli, two anisotropic moduli, and two polar angles. But these two polar angles can vary with the reference frame, but their difference is an invariant to the reference frame. They also allow me to express the elastic symmetries of a given material, such as isotropy, orthotropy, or the complete anisotropy, given several conditions and a given number of variables. In this study, I will take into account the orthotropic symmetries and the complete anisotropy of materials, but these other three symmetries are included in the orthotropy, so I take into account all of them. So what is orthotropy? When a material has two plane axes of symmetry, I have an orthotropic material. I can express an orthotropic material using polar parameters given 5 independent variables, the two isotropic moduli, the two anisotropic moduli, and one polar angle. The most important condition to follow for an orthotropic material is that the difference between the polar angle has to be either 0 or 45 degrees. And that's when we know we have an orthotropic material. The orthotropic domain can be defined using the geometric bound by 3 different inequalities. And we have an illustration of the orthotropic domain here, with the first inequality representing the right bound, the second one the lower bound, and the third one the upper bound of the domain. There are some particular families in this domain, such as cross-ply laminates that are defined on the right border of the domain that describe laminates with plies at either 0 or 90 degrees. We also have angle ply laminates at the upper border, which describe materials with sequences at plus and minus theta, and theta is just one angle that can be analytically calculated using the values of RK or R1. For example, the lower corner of my domain is a balanced angle ply laminate with the values of theta at 45, so either plus or minus 45 degrees. If I want to expand my domain to fully anisotropic, I will need 6 independent polar quantities. This time I have 3 anisotropic moduli. For anisotropic material, I have a thermodynamic limits of existence that was also valid for the orthotropic cases. But the geometric bounds of the anisotropic laminate that are described here by 4 inequalities are included in this thermodynamic limits. So we do not really need the thermodynamic limits of existence to respect, because once we respect this, we are already sure that the thermodynamic limits are respected. Here we have a representation of the anisotropic domain in the 3D form. We can see that if I cut the anisotropic domain in the RKY equal to 0 axis, I will obtain the same orthotropic domain that I had before. So the orthotropic domain is included in the anisotropic domain. So to conclude, the advantages of the polar parameters is that they are proper tensor invariants. They can express any type of plane tensor of any order and symmetry, for example, D tilde. And they remain limited to maximum 6 parameters. So I can express express coupled non-symmetric laminates with only 6 parameters, and they allow me to work with non-identical plies in material and thicknesses. So using these models, I can then proceed to the formulation of the optimization problem. As I said, I will conduct deterministic optimization, uncertainty quantification on the optimal cases, and finally a stochastic optimization. During this presentation, I will not talk about the optimization of variable stiffness laminates and uncertainty quantification of those laminates or even other laminates in details, but they are present in the manuscript if you're interested. The general formulation of the deterministic optimization can be expressed as the maximization of the flutter velocity. So we always want to avoid instabilities as far as we can. It could either be formulated using the direct approach by the ply angles directly, or by the multiscale approach using the polar parameters. The material that we use during this work has these engineering properties, and its polar parameters the polar parameters of the base layer stiffness tensor can be expressed using these 6 parameters. But throughout this work, I will always consider composite materials with layers of identical material, so all the plies of my material have the same material. So this is why the isotropic moduli are constant throughout the study. I will not change them. In order to formulate the optimization problem in the general anisotropic domain, I will use the anisotropic moduli that are treated as continuous variables, and their bounds are defined using the polar parameters of the base layer. I use one polar angle that is defined between minus 90 degrees to 90 degrees that is treated as a discrete variable with 1 degree discretization. And for the direct approach, I use ply angles that are discretized between minus 90 degree to 90 degree by a step of 5 degrees. So for the first case, I use ply angles as optimization variables, so I have the direct approach. But I only have 8 optimization variables because I consider a symmetric ply, so my 16 number of plies are divided by 2. For the second case, I use polar parameters as the optimization variable, so it's the multiscale approach. And in this case, we can see that I have a constraint in my optimization formulation, which defines the limits of my anisotropic bound, the geometric limit that we defined earlier. If I compare the results of the 2 cases, here we can see that I reach similar values in the flutter velocity for both cases, and also almost similar values for the flutter frequency. But if I go to the evolution of the maximum flutter velocity per generation, I can see that the polar parameters reach the maximum values faster than the ply angles. And if I look at the mean value of the flutter velocity per generation, I can see that the slope of the evolution of polar parameters is steeper than the ply angles, which can indicate that I investigate a larger domain with polar parameters than with ply angles. Comparing the elastic properties of both cases, the optimal case that I had with the ply angles has a difference between the polar angles of almost 45 degrees, which can indicate that my optimal case is almost orthotropic. This is not the case for the polar parameters, because the difference between the polar angles is 35 degrees, so it is more definitely anisotropic. But if I look at the diagram of the Young modulus, I can almost detect 2 axes of symmetry for the polar parameters. So I can say that both my cases resemble somehow to my orthotropic symmetry, so I will continue the rest of my study only in the orthotropic domain. In order to reformulate my optimization problem in the orthotropic domain, I use this time 2 anisotropic moduli that are again continuous and 1 polar angle. But I will add a new variable called alpha swept that defines the angle of my geometry, the swept angle of my wing, whether it's swept forward or swept backward. That varies between minus 45 degrees to 45 degrees with a discretization of 5 degrees. So the optimization formulation is defined again as the maximization of the flutter velocity imposed with a constraint that is imposed to the geometric bounds of the orthotropic domain. Here we have the results of the deterministic optimization. We can see that our optimal case falls exactly to a straight wing, which means that we reach the highest value of the flutter velocity for a straight wing with a phi1 that is -2, that is almost equal to 0, meaning that the maximum flutter velocity corresponds to a straight wing with an orthotropic axis that is aligned with the main axis of the geometry of the wing. We continued the same optimization process for 2 swept backward and swept forward cases. For the swept backward and swept forward cases, we don't optimize the swept angle anymore. They are fixed to -15 and 15 degrees, and they remain constant throughout the optimization problem. We can see that the flutter velocity of neither of the cases ever reaches as high values as the straight case, but something that was interesting is that the values of the phi1 for both cases is no more aligned with the main axis of the wing, which means that the value of the polar angle has a high influence over the maximum value of the flutter velocity. Here we place our 3 optimal cases over the orthotropic domain based on their anisotropic moduli. We can see that our straight case is based over the angle ply curve, our swept backward wing is placed over the cross ply border, and our swept forward wing is not far from the cross ply border, but it's not totally matched. If I compare the aeroelastic responses of the 2 swept cases for the second and third aeroelastic modes, the continuous lines represent the second and third aeroelastic modes of the swept backward wing, and the dashed line for the swept forward wing. We can see that the swept backward wing becomes unstable later than the swept forward wing, but for both cases, I can see that the second and the third mode become unstable almost at the same time, at the same velocity. If we look at the mode shapes of the unstable modes, we can see that for the swept backward wing, we have the third aeroelastic mode, and for the swept forward wing, we have the second aeroelastic mode that becomes unstable. But again, it's only a matter of few meter per second for the next mode to become unstable. So as I said, for the multi-scale approach using the polar parameters, I have 2 steps. One step by optimizing the polar parameters, and the second step during which I need to retrieve the stacking sequence that corresponds to these optimal polar parameters. So for my 3 cases, as I said, we have my 3 optimal polar parameters, but then I have to find the corresponding stacking sequence. For the straight wing, we are over the angle ply curve, so it's easy to obtain the stacking sequence analytically. It's equal to 38 degrees. By deviating it to the polar angle, we obtain our final stacking sequence here. But for the 2 other cases, I cannot calculate their stacking sequence analytically, so I have to do it numerically. I use a function called the callback-Leibler function that measures the difference between 2 tensors. The tensor that I try to calculate is defined as the combination of the 3 tensors of rigidity that we had earlier. The T here, the T subscript describes the target tensor that corresponds to our target polar parameter. So the set of optimal polar parameters are set as our targets. Then I minimize this function by giving different values to my L theta and compare it to my target polar parameters until I have a minimum value, thus a corresponding stacking sequence. I conduct this optimization problem for the swept backward wing that is over the cross-ply border, so I limit my theta values to only 0 and 90 degrees. But for the swept forward value, I allow the theta to vary between 0 to 90 degrees every 1 degree. Here is the final results for both cases, and I compared the anisotropic modules and the flutter velocity and flutter frequency to the target polar parameters, and we saw that the differences are very small. So we can say that we have successfully obtained a stacking sequence that is equal, that corresponds to our polar parameters. So in conclusion, during the deterministic optimization, I conducted two optimizations, first in the anisotropic domain, second in the orthotropic domain for 3 different geometries. I retrieved their corresponding stacking sequence for each of the geometries, but something that we noticed was that for almost all the cases, either the second and the third aeroelastic mode become unstable at the same time, or the third mode is really close to instability when the second mode becomes unstable. So our question was, how does a small perturbation could alter this type of behavior? This is why we first started by conducting a parametric study in the orthotropic domain. By orthotropic domain of a straight wing with phi1 equal to 0. So we calculated the flutter velocity for all of the laminates in this domain, and we can see that we obtain a discontinuous domain with one modal region that corresponds to the second aeroelastic mode that becomes unstable, and another modal region with the third aeroelastic mode that becomes unstable. Our maximum flutter velocity is right next to this discontinuity, and we think this is why the switch between the second and the third mode occurs during our aeroelastic response. In order to verify that, we conducted an uncertainty quantification analysis over the corresponding stacking sequence to this point. We imposed 5-degree uncertainties over each pi angle, and we obtained this final PDF of the flutter velocity, and we can clearly see that it's bimodal with one peak near the values of the maximum flutter velocity and another peak near the values of the velocity on the other side of the discontinuity. Our maximum flutter velocity corresponds to almost 147 meters per second, and with the current standards in the industry that are empirical, the safety margin taken from this maximum value is only 15%, which gives place to a design velocity of 125 meters per second, but this design velocity falls exactly on top of the second peak, and it remains all this probability under the curve for flutter velocity to occur during my flying regime, which is about 25%. So what we wanted to do was to increase and avoid this big probability to fall into our flying margin. So we decided to include our parametric uncertainties during the optimization process. To do that, we decided to work with reliability-based design optimization. That is one type of stochastic optimization. We want to minimize the probability of having a flutter velocity below a given design velocity, and we use pi angles as optimization variables. We have multiple difficulties doing that. The first is the computational time, because the PDF that I showed you in the previous slide required only 1,000 samples, and it took about 12 hours over 30 cores. Which during an optimization process could become very costly. This is why we decided to use a surrogate model in order to reduce our computational time by only calculating a few number of samples. But the problem with surrogate model is that they cannot treat a discontinuous function, and we clearly saw that our response surface is discontinuous. There are various methods to overcome these limits, but we found in literature a continuous function that could replace our flutter velocity and allows us to reduce our computational time even further. The second problem of working with the surrogate model is the dimensionality of our problem. As I said, we have 16 plies, which gives place to 16 uncertain parameters at least, and the dimensionality of problem could be very high. This is why we want to use with polar parameters that are only 6 uncertain parameters to reduce these number of uncertain parameters. The surrogate model that we use is the Gaussian process regression using a radial basis function kernel. But again, as I said, we need a continuous function, and the function that we use is called the stability margin. Stability margin can be formulated as the negative value of the maximum aeroelastic damping at a given design velocity. So if I want to illustrate it over this aeroelastic damping diagram, if I set myself at a design velocity of 105 meters per second, my stability margin is this distance between the zero axis to the maximum damping value of my mode, of any of the modes. Another advantage of working with stability margin is that, as I said, we only compute our aeroelastic system, our PK solver, at one given design velocity. So we calculate dampings at one design velocity, which further reduces our computational time instead of reiterating over multiple velocities. Here we have computed the same response surface as we had before for the flutter velocity, but this time for the stability margin at a design velocity equal to our maximum flutter velocity here, and we can see that it gave us a continuous response surface instead of our discontinuous one that we had before. So if I want to reformulate my optimization, my stochastic optimization problem using the stability margin, this time I will minimize the probability of having negative values of the stability margin at a given design velocity. I compare the PDFs of the stability margin and the flutter velocity that I had for my deterministic orthotropic case at a given at the design velocity of 125 meters per second. So now this area under the curve will be translated to the area in the negative region under the curve for the stability margin. This is my algorithm for the reliability-based design optimization using ply angles. First, I generate an initial population using my genetic algorithm. Each stacking sequence will then enter my solver, and I generate two sets of random variables, two sets of samples. One smaller set of samples called the training sample, and one larger set of samples for which I want to predict the dampings. For the training samples, for both cases, I calculate their corresponding polar parameters. For the smaller set, I compute the eigenvalues S, and I sort them using a function called MAC. Then I will fit my surrogate model to the aeroelastic dampings of the smaller set, and then I will run my surrogate model for the larger set of set, and I predict my dampings and calculate my stability margin and try to minimize the probability of failure using my genetic algorithm. If I do that for 3 different design velocity of 120, 125, and 130 meters per second, I can see that my probability of failure, so probability of having negative stability margin, increases with my design velocity, but my flutter velocities remain around the same values. I can see the increase of the probability of failure here on the diagram of the stability margin, on the PDF of the stability margin. But on the PDF of the flutter velocity, we can see that if I calculate my 0.1th percentile flutter velocity, this value increases with my design velocity. So I can say that I can gain in my performance when I increase the value of the design velocity during my optimization. Comparing the optimal case obtained by the reliability-based design optimization at a design velocity of 125 meters per second to the initial deterministic orthotropic case that we had for a straight wing, we can see that we have significantly decreased the probability of failure from the orthotropic case to the reliability-based design optimization case. And if I look at the flutter velocity PDF, I can see that before I used to have a bimodal case. I used to have a bimodal PDF that now has clearly turned into a single peak PDF, and I still have the mean value of the flutter velocity for the reliability-based design optimization case that is higher than the deterministic case. The probability of failure has decreased from 25% that we had before to only 3% in this case. To conclude, we conducted a stochastic optimization using ply angles, and we significantly reduced the probability of failure. But the problems that we had doing that was that the results were not repeatable. For example, for a given design velocity of 130 meters per second, We launched the same case 3 times, and we did not obtain the same fiber orientations or elastic properties for similar values of the probability of failure, which means that I have very non-convex problem, and it's hard to have a repeatable result. Our answer to that was to use polar parameters as optimization variables, as we had earlier, which allows me to even have more control over my elastic properties of my optimal laminate. In order to do that, as I said, we replace our optimization variables by polar parameters, but the problem is that we cannot impose physical uncertainties over polar parameters, the 5-degree uncertainties that we had on the angles. So we decided to find a solution for that by adding the stacking sequence retrieval step in between the population generation and entering our solver. So the population of polar parameters generated by my genetic algorithm, for each of them, I will conduct a minimization of the callback Libler function. I will find the matching stacking sequence, which will then enter my solver, and the rest of the algorithm will continue on similarly as before. Here I have compared the results I obtained by the angles and the polar parameters. I can see that using the polar parameters, I have further reduced the probability of failure. I could even, using the polar parameters, I have limited my optimization domain to only orthotropy. So now I have more control over my elastic properties. And I can see that I have even increased the values of my flutter velocity from 137 to 144. On the PDF of the stability margin, we can see that the probability of failure has clearly decreased. And on the PDF of the flutter velocity, we can see that now we have a wider PDF for the flutter velocity, but the mean value of the flutter velocity is still higher for the polar parameter case compared to the apply angles. If I compare the aeroelastic response of the 2 cases, I can see here the gap between the unstable modes. But for the polar parameters, I have the 3rd mode that becomes unstable, as we can see here. And for the apply angles, I have the 2nd mode that becomes unstable here, as we can see. So something we did during this reliability-based design optimization is that we have increased our flutter velocity. We still have this mode switch between the 3rd and the 2nd mode, but they are around the same value of the flutter velocity, so the mode switch does not bother us as much as it did before. So to conclude, I have conducted a deterministic optimization in both fully anisotropic and orthotropic domain. I did it for 3 different geometries, and I retrieved their corresponding stacking sequence, but we saw that we have this problem of mode switch that exists for all of our optimal cases. And this is why we decided to conduct a stochastic optimization while taking into account the parametric uncertainties. During the optimization problem, when we did that, we removed the lower peak of our bimodal PDF. We reduced our probability of failure, and in order to go further, we used polar parameters to have more control over our elastic properties, and using the polar parameters allowed us to create the most general optimization process that we could achieve. We could improve our study by studying more complex geometries with the existing models, aerodynamic and structural models. We could study T-tail wings or simple whole body airplane bodies, as we can see here, that were done previously in the literature. We could also use multi-fidelity methods to enhance the precision of our model, both in aerodynamics or structure. We could also use lower fidelity methods in the optimization process to detect the regions of our interest, and then a higher fidelity method with the gradient methods in order to achieve our absolute value of optimum case. We could also work on flutter control to surpass some hump modes that existed in our deterministic cases, or eliminate the low probabilities of flutter events that still remained in the PDF of our reliability-based design optimization cases. And thank you for your attention.